Hello guys, in a continuation with the chemical equilibrium, we are going to discuss today the effect of temperature, then the effect what happens at equilibrium for the vapor density when the reaction is a gaseous state, and a very important principle which we are going to discuss, that is Le-Chatelier's principle. Now, first of all, we will consider the effect of temperature. So, as we know the meaning of exothermic reactions and endothermic reactions, let us consider a reaction which is taking place with the evolution of heat. That means, let us consider a reaction which is exothermic reaction. So, if we plot a graph of energy, so basically potential energy versus rate of reaction or reaction coordinate as the reaction progresses, how the reaction is progressing. So, if I consider a reaction, A gives a product B, where delta H, that is the heat of reaction, is considered to be minus Q kilojoule. So, if we plot a graph, obviously certain amount of energy is associated, so that potential energy, if we plot a graph for a reaction, we are getting a graph like this way. So, the energy difference between reactants and products, rather this one, that is called as delta H. Now, interestingly, if you observe carefully, the reaction is not taking place directly. We are supplying certain amount of energy to the reactant A, and after a particular amount of energy, so let us consider this much amount of energy. So, if I consider this energy, okay, the highest amount of energy, after that the energy goes on decreasing, that means here onwards the product starts forming. Now, this is for the forward reaction. This is for the forward reaction. So, whenever a reaction is taking place, certain amount of energy has to supply, and that energy is called as activation energy. So, let us consider this is EA for the forward reaction. Now, suppose that product is also converted into reactant, means if there will be a backward reaction, then again that B, this is product B, has to achieve this much amount of energy. So, let us consider that may be E dash A. So, activation energy of the product. So, what is delta H in that case? EA minus E dash A. Okay. So, delta H is equal to EA minus E dash A. Now, how this explanation help us to understand the effect of temperature on equilibrium? There was a scientist, Arrhenius, who has given one equation that relates the equilibrium constant, rather rate constant, with temperature, and that expression which he has derived numerically is K is equal to AE raised to minus EA upon RT. So, similar equation you will be studying in chemical kinetics. K is a rate constant, K is equal to rate constant, A is called as a pre-exponential factor or Arrhenius constant, EA is called as activation energy and T stand for temperature. R is a universal gas constant. Now this is for a particular reaction. This is not for the equilibrium constant. This is a rate constant. So rate constant and equilibrium constant are two different things. Okay. So when the forward reaction is taking place, in that case rate law expression is rate is directly proportional to concentration of A. In that case the constant which we are getting, that is called as what? Rate constant for the forward reaction. Similarly we can plot rate constant for the backward reaction. Okay. So if I consider only the forward reaction, so I can write K forward is equal to AE raised to minus EA upon RT, because EA is the activation energy for that. Okay. Now if I take a log, then I will write log the base E, then we can write log A. Okay. So here minus EA upon RT, so we are getting minus EA upon RT log E to the base E is equal to 1. Similarly, for a backward reaction, I can write it as log to the base E Kb. So rate constant for the backward reaction is equal to log A minus E dash A upon RT. So here we have a activation energy for the backward reaction. Okay. So now I will do this way, log Kf minus log Kb, simple and straightforward, just I am subtracting, so log A get cancelled, minus EA upon RT minus plus E dash A upon RT. Okay. So this become log Kf upon Kb, so this is all to the base E only, is equal to minus into bracket we can write it as what, EA upon RT minus E dash A upon RT. So this is nothing but equilibrium constant. We already derived the rate law expression, applying law of mass action. So the ratio of rate constant for the forward reaction to the rate constant to the backward reaction is called as equilibrium constant. So log K equilibrium, so to the base E equilibrium is equal to minus 1 upon RT. Now from this expression I can write this as what, delta H. So we are getting a new expression now. So if I have to convert into log to the base 10, so I can write it as minus delta H upon 2.303 RT. So this clearly indicates how equilibrium constant depends on temperature if delta H remain constant. Okay. So we can calculate equilibrium constant at different temperatures by using this expression. So this is actually derived from Arrhenius equation. This is a one thing. Now here there are some problems related with to determination of equilibrium constant, or rather sometime we can use this expression to understand the effect of temperature. So if there is a exothermic reaction, then how is it going to, how temperature affect the direction of the reaction also. Okay. So there are certain questions based on theoretical as well as the calculation approach also there on this kind of a equation. Now similar kind of a problems will be there, but there will be those problems will be there in a chemical kinetics, but there we are using rate constant. So you have to mind that difference. Here we have to consider whenever there is an equilibrium constant, delta H will be there, and whenever there will be rate constant, activation energy will be there. So that thing you have to remember. Now, we will consider now dissociation, degree of dissociation, how to calculate degree of dissociation. So, calculation of degree of dissociation with respect to vapor density. So, let us consider a reaction. A reversibly gives you NB. Okay. So, initially we have suppose 1 mole. So, since there is no dissociation, so this must be 0. Okay. Then at equilibrium, so if alpha is the degree of dissociation, then 1 minus alpha will remain at equilibrium, and how much B will form? N alpha. Okay. Now, initial volume. So, let us consider that is V liters or VML, and total number of moles at equilibrium is equal to 1 minus alpha plus N alpha. Okay. So, this I can write it as 1 minus alpha into bracket 1 minus N. Okay. This way we can write. Now, therefore, volume at equilibrium is 1 minus alpha into 1 minus N times V. Now, vapor density, let us consider capital D, that is a vapor density before dissociation. And that is inversely proportional to V, and small d is a vapor density after dissociation at equilibrium. So, that is also inversely proportional to 1 minus alpha into 1 minus N times V. So, if we take the ratio, d by d is equal to, so we can get it as 1 upon V divided by 1 upon 1 minus alpha into 1 minus N times V. So, that becomes 1 minus alpha into 1 minus N. So, if you solve, you will get the expression for this. So, I can write it as d minus d, okay, minus 1 is equal to minus alpha into 1 minus N. Okay. So, we are taking minus 1, yes, it is correct. Then further we can write this as 1 minus d by d is equal to alpha into 1 minus N. So, the expression become d minus d upon d into 1 minus N is equal to alpha. This is the expression for the degree of dissociation at equilibrium. Okay. So, now we know that vapor density is equal to molar mass divided by 2. So, if you put the expression before and after, we will get another expression that will give you idea about degree of dissociation. Now, this d stand for molar mass initially. So, molar mass of A, and this small d. So, from this d we can get the initial molar mass. Okay. So, let us consider that capital D becomes capital M by 2. So, capital M is the molar mass of the reactant, and small d is nothing but equilibrium, molar mass at equilibrium. So, we can write it as small m by 2 minus capital M by 2 divided by 2 into 1 minus n is equal to alpha. Okay. So, the equation becomes m minus capital M, okay, divided by m small m into 1 minus n. So, this is the expression for the degree of dissociation in terms of molar mass before equilibrium and at equilibrium. Okay. So, there are certain problems which may they ask you on the basis of dissociation. Okay. So, more about the things about the Le Chatelier principle we will discuss in the next session. Thank you.